Hello, welcome back to the class. So we'll go with the next design problem. Please write down this problem. A reinforced concrete beam is supported on two walls, 750 millimeter thick spaced at a clear distance of 6 meters. The beam carries a superimposed load of 9.8 kilonewton per meter. Design the beam using M20 concrete mix and HYST bars of Fe415 grade. So solution. So these are the design steps. So that is determination of dimensions, calculation of design bending moment, MUD, to check the adequacy of depth to calculate the area of tension steel AST required next step is check for shear, next check for deflection, that is point number 6. And the last one is reinforcement details. Let us go with the first one. What is the first step? Determination of dimensions. That is what is the meaning of determination of dimensions? We need to determine, so what are those cross-sectional dimensions? Breadth and the depth. So before going further, let me read the problem for you. A reinforced concrete is supported on two walls, 750 millimeter thick, spaced at a clear distance of 6 meter. Clear distance. Okay, this is not effective distance. This is clear span of 6 meter. The beam carries a superimposed load of 9.8 kilonewton per meter. Superimposed load is nothing but the live load. Design the beam using M20 concrete mix and HYSD bars of grade Fe 415 steel. Here first I draw the figure. Please write down the figure. And the width of the support on each side is 750 millimeter. So clear span, or whatever the problem says, a clear distance between two supports is 6 meter. That is measured from inner face of one support to the inner face of the other support. And the resulting reaction on this support is going to be acting exactly in the midway of 750 millimeter. Similarly on this side. Okay. See, determination of dimensions. Look here. Superimposed load is given 9.8 kilonewton per meter. That is live load. So when we are designing, not only should we include the live load, but also we should include dead load as well. Here there is no other dead load given. Any other dead load like wall dead load, everything, that is not given. So once that is not given, we are not going to take it. However, we have to include the self weight of the beam. Okay. So self weight of the beam, if you need to include, then what you need is, you need the dimensions, overall dimensions. Do we have the overall dimensions of the cross section? This is a design problem. You need to find out everything from the beginning. After all, the design is finding out what are the dimensions of a beam required, and also what are the tension steel and what are the stirrups we need. So that's what the design is. Here we don't know. Unless we find out the cross-sectional dimensions of the beam, so we cannot find out what is the dead load. Is it clear to you? So, the first step is determination of dimensions. So, we are going to estimate what is B and what is D. So, by using thumb rule, the effective depth is going to be 1/15 of the span to 1/10 of the span. Okay. So 1/15, see, when we use thumb rule, okay, it is not necessary that we should always use effective span here. Sometimes we may use effective span, sometimes we may use clear span. So it's okay, because we are going to get two values and we can pick up a depth, convenient depth between those two values. Okay, 1/15 of span, here it is 6 meter is the clear span. Even if you take effective span, that is, sorry, center to center distance of 6.75 meter, that is also fine. So here I am taking only 6 meter, that is 6000 millimeter, that is 400 millimeter, and 1/10 is okay. So look here. So I can pick up a depth, total effective depth, okay, between any value between 400 and 600. So what I do is, so let me consider an effective depth equal to 400 millimeter. 400 millimeter. So effective depth of the section is measured to the centroid of the tension steel from the compression zone, that is D. And of course, we are going to provide stirrups. Okay. So what is the overall depth? So overall depth D is the effective depth plus the effective cover. And the effective cover is going to be measured from the tension zone to the centroid of the tension steel. So if you remember, by assuming moderate exposure of concrete to the atmosphere, clear cover to the reinforcement, that is the stirrups, is 20 mm. And let us assume that we are using 8 mm dia stirrups, and let us consider 20 mm dia tension steel. Then what is the effective cover? As I said, effective cover is going to be measured from the edge of the tension zone to the centroid of the tension steel. That is, for a mild exposure from the code book, it is 20 millimeter plus diameter of the stirrup plus half the diameter of the tension steel. That is going to be the effective cover. Therefore, total depth equal to effective depth 400 plus clear cover plus dia of stirrup plus half the diameter tension steel of the dia of tension steel, that is equal to 400 plus clear cover is 20 mm plus dia of stirrups is 8 because we are using 8 mm dia stirrups, and half the diameter of tension steel. What are the diameter of the bars we are considering here? In the previous examples, yes, we took 16 millimeter diameter bars. In this case, we are taking 20 millimeter diameter bar. So it is 20 by 2. Okay. So what is the sum? That is equal to 400 plus this much, that is 38, 438. 20, 28, 20 by 2. That is the overall depth, but we are not going to provide that fractional value as overall depth. Say 450 millimeter. 450 millimeter. So once you increase the overall depth from 438 to 450 millimeter, even the effective depth changes. So what is going to be the actual effective depth? That is going to be the actual total depth we are providing minus the effective cover, that is this. This remains the same. Therefore, actual effective depth, okay, equal to actual effective depth, D equal to, so overall depth we have provided is 450 minus the effective cover, 20 plus 80 plus 20 by 2, that is equal to 412 millimeter. That is the effective depth we are providing. So now this dimension is fixed, overall dimension is fixed. So what is left next? What is the width? Normally what we do is, when it comes to the width, we are going to consider the width of the beam as 1/3 of the total depth equal to 150 millimeter to 2/3 of the total depth, that is equal to 2/3 into 450, that is equal to 300 millimeter. So you can pick any width between these two, including this or this. So therefore, let us consider the width of the beam B equal to 300 millimeter. Okay. So now D is fixed. What is this? 450 millimeter. So width is 300 millimeter and the effective depth is 412 millimeter. Okay, now we know the dimensions. Okay, so once we know the dimensions, we can find out what is the dead load. Live load is already given, 9.8 kilonewton per meter. For that, we need to add the self weight of the beam to find out what is the design moment finally. Okay? Next is calculation of design bending moment MUD. Under that, the first step is the calculation of the load, to find out the effective span. That is the first step. The effective span. So effective span, as per the code, effective span is lesser of the following two cases. As per the code. Okay, just to remind you, please open the code book on page 34, 22.2a. Please open it. 22.2a. It says for simply supported beam or slab. Okay, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of slab or beam, or center to center of supports, whichever is less. So I have discussed this in the previous example, just I am trying to refresh your memory. So it is lesser of the following two cases. What are those two cases? The distance between the centers of two supports, so that is the distance. Okay, so what is that distance? 6 meter, that is a clear span plus half the width of the support width of the support two times. The reason is we have got two supports. So half the width on this side and the other half on the other side. So that is 6 meter plus 2 times half. So what is the width of the support? That is 750 millimeter. So we have this value in meter. So I am going to substitute 750 millimeter in meter, that becomes 7.75 meter. Okay, that is equal to 6.75 meter. And the next case is clear span plus effective depth. So what is the clear span? Of course, 6 meter plus what is the effective depth we have provided? 412 millimeter. That is 0.412 meter. That is 0.412. That is equal to 6.412 meter. So we have two values. The code says take lesser of those two values as the effective span. Therefore, effective span LE equal to 6.412 meter. Okay. So this is the effective span that is calculated. The next step is to find the self weight of the beam. To find the dead load. So in this case, dead load is the self weight of the beam, there is no other dead load. Okay, I am going to call that dead load as WD. Okay. So dead load of the beam, I don't say dead load, self weight of the beam equal to area of cross section of the beam multiplied by the unit weight of reinforced concrete. Okay. So what is the area of cross section of the beam? This is the width and this is the depth, total depth. See, when you are considering the self weight of the beam, you should not consider the effective depth. Instead, you should consider the overall depth. So the overall depth is 450 millimeter. So I am going to find out the area of cross section of the section, that is 0.3 meter multiplied by 0.45 meter. So I am converting everything into meter, so that I am going to get the area of cross section in terms of meter square. So what is the unit weight of RC? That is 25 kilonewton per meter cube. If you refer IS 875 part 1, so you are going to get the unit weight of reinforced concrete equal to 25 kilonewton per meter cube. Okay. So after simplification, you are going to get the value equal to 3.375 kilonewton per meter. I hope you understood. This is kilonewton per meter cube. When we are putting the value in terms of kilonewton per meter cube, these two values should be in meters. Okay. And the self weight of the beam is 3.375 kilonewton per meter. So I call this as WD, not capital WD, it should be small WD. Okay. Therefore, the total service load, so I am going to call this as W, okay, is superimposed load. You can call this as WI or WL. I stands for superimposed, L stands for live load. So whether it is superimposed or live load, it is one and the same. Okay, superimposed load plus dead load. That is the self weight of the beam in this case. So what is WI? Here it is given 9.8 kilonewton per meter. That is 9.8 kilonewton plus what is WD? That is 3.375. Okay. Therefore, W equal to, that is 13.175 kilonewton per meter. Okay, so it is 800, 13.175 kilonewton per meter. That is the total service load. Okay, but we are not supposed to take this load as it is on design. No. In limit state design, what we have to do is we have to multiply each of these values by their corresponding load factors as given in the code book. Okay, here the load factor for the imposed load, that is for the live load, is 1.5, and for this it is 1.5 as well. So because I have the load factor, same load factor for these two, I have added this and I am going to multiply this value by 1.5 to arrive at the design load. In case the load factors differ for live load and dead load, then to arrive at design load you must multiply this value by that particular load factor, say 1.7. For this, say it is 1.4, then you have to multiply 1.4 with this. So when you add that, then you are going to get the design load finally. Okay, here same 1.5 for dead load and 1.5 for live load. So I have added these two numbers. This is the total service load. Therefore, the design load, I am going to call that value as WED is 1.5 times, that is gamma F multiplied by W, that is 1.5 times 13.175. Okay, that load comes to 19.76 kilonewton per meter. Okay, so this is the design load, or you can call it as ultimate load or factored load. They are one and the same. Is it clear to you? So now we have the span, that is the effective span, and we have the design load. So we will go with the next step. .76 kilonewton per meter, and the effective span is 6.412 meter. Okay, this is the final loading beam or loaded beam, and it is loaded with the design load. So this is the calculation of design bending moment. Therefore, design bending moment, I am going to call that design bending moment as MUD, that is WUD LE square by 8, okay, where LE is the effective span So that is 19.76, 6.412 square divided by 8, that is MUD equal to 101.55 kilonewton meter. 101.55 kilonewton meter, or MUD equal to 101.55 into 10 to the power of 6 Newton millimeter. Okay. So this step is over. That is calculation of design bending moment MUD value. What next? To check for the adequacy of depth. To check for the adequacy of depth. What it means? See, by using thumb rules, we arrived at the overall depth of the beam as 450 millimeter. So by taking out effective cover, the effective depth was 412 millimeter. Okay, but we are not sure that depth is adequate to take care of the design bending moment of 101 point something, that is 101.55 kilonewton meter we just calculated. In case the depth of 412 millimeter is not adequate, then we have to go back and increase the depth, and also we have to do the designing from the beginning. So first we are going to check. So we are going to check the adequacy of depth against MU limit value. If you open page number 96 of the code book, we have MU limit equal to 0.36 XU max by D, 1 minus 0.42 XU max by D multiplied by BD square FCK. Is it not? So open page number 96. That is under 1.1 C. That is 1.1 C, page 96. Okay. So for MU limit value, we are going to substitute the value of MUD. We just now calculated. That is 101.55 into 10 to the power of 6 equal to 0.36. If you remember, XU max by D for Fe415 steel, what is the value? That is 0.48 from page number 70. That is 0.48. 1 minus 0.42 into 0.48, and what is the value of B? So we are going to take the value of D as it is. So that is 300 millimeter, and D square, that is the value we are trying to find out. What is the minimum effective depth required? Multiplied by FCK is 20. So after simplification, we get D equal to 350 millimeter. So that is the depth required, 350 millimeter is the depth required for a balanced section. So therefore D required equal to 3 for a balanced section equal to 350 millimeter. Minimum depth, minimum effective depth we have to provide is 350 millimeter. But in reality, how much we have provided? Therefore, actual depth provided is D, that is equal to 412 millimeter, which is greater than 350 millimeter required. Therefore, the depth provided is adequate. Okay, and one more thing, when we are providing more than the balanced section depth, automatically we go for under reinforced section. The section is going to be under reinforced. Is it clear to you? So we will go with the next step. And in this step, to check for adequacy of depth, what we did was we made use of the formula of mu limit equal to something as given in 1.1c on page 96 of the code book. So when we calculated the minimum effective depth required to take care of flexure, we got the value of D required equal to 350 millimeter, but D provided was 412 millimeter. So we provided more than what it was required. So once we increase the depth, what happens is the lever arm increases. To resist a given moment, if you increase the depth, then you need less area of steel. That gives rise to under reinforced section. So in this case, 350 was the minimum required for a balanced section, and 412 was the effective depth provided. So it was under reinforced. That's why I am going to make use of the formula of under reinforced section given in 1.1b to calculate the area of steel required. Okay. Therefore, we have mu equal to 0.87 FYASTD 1 minus ASTFY divided by BDFCK. This is the formula we have. Okay. And by substituting the known values here, and for mu we have to substitute the value of the design bending moment we got due to the external load. So what was the value? That was 101.55 kilonewton meter. Convert that value into Newton millimeter, that is equal to 0.87. Fy is 415 multiplied by AST, we don't know, that's what we are trying to find out, and D is the effective depth provided, 412 1 minus AST into 415 divided by 300 is the breadth, 412 is the depth, and for M20 concrete FCK value is equal to 20 Newton per millimeter square. Okay. So on further simplification, we are going to get the equation like this. AST square minus 5956.56 AST plus 4.066 into 10 to the power of 6, that is equal to 0. So this is in the form of AX square plus BX plus C. So by solving for AST, we get AST equal to 786.44 millimeter square. Okay. So that is the minimum area of tension steel we need. Okay. So let us use 20 mm diameter bars. 20 mm diameter bars. Therefore, number of 20 mm diameter bars equal to total area required 786.44 divided by area of each bar, that is equal to 2.5. Of course, we cannot provide 2.5 bars, so we are going to provide 3 bars, say 3 bars. Okay. So once you provide 3 bars, so the actual area of steel we are going to provide is going to increase. It is not going to be this value anymore. Therefore, actual area of steel provided, again I am going to call that as AST itself, 3 multiplied by pi by 4 20 square, because we have 3 bars. That is equal to AST equal to 914.50 millimeter square. Okay. So this is the actual area we are providing. Next thing is we have to check for AST minimum and AST maximum. Check for AST minimum. AST minimum. So from 26.5.1.1a, page, I think it is 47, page 47. So we have AST minimum divided by BD, okay, equal to 0.4 divided by AST FY, AST minimum BD FCK, that is equal to 0.85 divided by FY, 0.85 divided by FY. So when you are writing this in the examination, it is not necessary that you have to write all these things, no. So whatever I have written here, that is purely for your reference. Is it clear to you? So in the code book, if you go here, if you look at this formula, they have given only as AS. So that is nothing but AST minimum. So I have called this as AST minimum. Therefore, AST minimum equal to 0.85 divided by FY multiplied by BD. That is equal to 0.85. FY is 415, B is 300, D is 412. That is equal to 253 millimeter square. That is the area of minimum area of tension steel required. So this is, therefore, AST is greater than AST minimum. Therefore, okay. So what is the actual AST? 914.50. What is the minimum we have to provide? 253 millimeters square. What it means is, in case this value is say 200 millimeters square, what is the AST minimum value? 253. So in such case, what we do is, we are going to go ahead and provide at least 253 millimeters square area of tension steel. So that is done to avoid brittle fracture of steel. Okay. In this case, yes, we are okay. Similarly, we have to check for AST maximum. To check for AST maximum. Again, from 26.5.1.1b on page 47, AST maximum equal to 0.04 BD. D is capital. We need to consider the overall depth, but not the effective depth. So it is 0.04. 300 is the breadth, 450 is the depth, that is equal to 5400 millimeters square. This is AST maximum. So AST maximum is greater than AST we are providing. Therefore, okay. So in the previous case, I am going to remind once again, in case this value goes below AST minimum, we go ahead and give at least this much of area. But when you check for AST maximum, in case this value goes beyond 5400 millimeters square, that is, say, this is say 5500 millimeters square, which is greater than 5400 millimeters square. In such case, so you should not go ahead and provide 5400 millimeters square. Instead, what you have to do is, you have to go back and increase the section size. Now we have provided 300 millimeter width and 450 millimeter overall depth. So that area is not adequate, okay, to take care of the steel, that is to put the steel. So in such a case, what we do, again as I said just now, so go ahead, increase the section size, okay, breadth and depth, or this or this or both. Then redesign the section, calculate the self weight once again, find out the new design bending moment, find out what is the area of steel required, actual area of steel required. Then again check that AST actual area of steel required with AST minimum and also check with AST maximum. Is it clear to you? Next, check for development length. Check for development length, LD. So from 26.2.1 page 42, let me reconfirm it. Yes, it's correct. LD equal to phi sigma s 4 tau BD. Okay. So find out what is the value of LD. So if you go to again 26.2.1 page 42, phi is the diameter of the bar we are providing. sigma s equal to 0.87 Fy, and 4 and tau Bd is the bond strength of concrete. So what is the value we should take? Again, go to page number 43 of the code book. Look at the top. Look at the top. At the top there is a table under 26.2.1.1. There is a table. So for M20 concrete, if you refer, tau Bd value equal to 1.2 Newton per millimeter square. So that value is for mild steel bar. When you are using HYSD bar, the surface is rough. In case of mild steel bar, the surface is smooth. So it will have a bond strength of, design bond strength of 1.2 Newton per millimeter square. When it comes to HYSD bar, the surface will be rough. So as a result, the design bond strength will increase. We can increase that value by 60%. So where it is given, again if you go to page number 43, first column, under 26.2.1.1, in the first column, if you read the first two lines, which I am going to read now for you guys, for deformed bars conforming to IS 1786, these values shall be increased by 60%. So whatever the values given in the table just above the lines, so you can increase those values by 60%. Okay, as I said, for M20 concrete it is 1.2 Newton per millimeter square. So I am going to multiply that 1.2 by 1.6 because I am increasing the value by 60%. So this is the diameter of the bar, 20 millimeter diameter, that is phi value. Okay, just I am going to write one more step, phi 0.87 Fy divided by 4 tau Bd. That is equal to phi is 20 millimeter diameter bar, 0.87 into 415 divided by 4. So tau Bd value from again 26.2.1.1, from that table it is 1.2 Newton per millimeter square. I am increasing that by 60% for HYSD bar. So this is 1.6 multiplied by 1.2. Finally, I am going to get this value equal to 940 millimeter. Okay. So this is from 26.2.1.1 page 43. Okay. This is the development length. Again, if you go to page number 44, please go there. So under 26.2.3.3, positive moment reinforcement, at least 1/3 the positive moment reinforcement in simple members and 1/4 the positive moment reinforcement in continuous members shall extend along the same face of the member into the support to a length equal to LD by 3. So what it means is, I explained this in the previous example. I am going to refresh your memory. This is the beam and this is the support of 750 millimeter, support width is 750 millimeter, okay, and we have 3 bars of 20 millimeter diameter . So if you look here, I have not curtailed any bars here. That means I have not cut any bars. What I have done here is I have continued all the 3 bars into the support. But the code says, so in case of simply supported, at least 1/3 the number of bars should be continued here into this support. So we have 3 bars, okay. So as per the code we can only continue and we can cut 2 bars. But practically speaking, we need at least 2 bars. Okay. So those 2 bars should be continued here, and if you need, you can cut one of the 3 bars which is in the middle somewhere here, because we don't need all the 3 bars to take care of bending moment here, because we have minimum bending moment here. Okay, we design the bending moment, we design the section for bending moment at the midsection where we have maximum bending moment. Okay, for that we got 3 bars. So development length, so that is measured from the face of the support. That's what the code says. So from the face of the support, the bars at least 1/3. Here I am not taking only 1/3. I am taking all the bars into the support. So that should be continued for a distance equal to LD/3. From here, it should be at least LD/3. So what is LD here? It is 940 millimeter. Therefore, LD/3 equal to 940 divided by 3, that is equal to 314, say 315 millimeter. Okay, that is as per 26.2.3.3a, page 44. Page 44. So what it means? You have to continue this bar at least for a distance equal to 315 millimeter. But how long we have continued? This is 750 millimeter. If you take the side cover, side effective cover for the steel here 50 mm, so we have extended the bar for a distance equal to 700 millimeter. Okay, that 700 millimeter provided is greater than the minimum required of 315 millimeter. So we are okay. Okay, so here I am going to show the side cover of say 40 mm. Okay, so therefore actual development length measured from the face of the support equal to support thickness 750 millimeter minus the side effective cover, that is 40 mm, that is equal to 710 millimeter, that is the actual effective depth provided. This is greater than LD/3, greater than LD/3, that is equal to 315 millimeter. Therefore, okay. Is it clear to you? So here once again keep in mind, I am not curtailing any bars. So I am going to repeat, I am not curtailing any bars, I am continuing all the 3 bars up to this point. If at all you cut some of the bars out of those 3 bars we have here, so I am going to show you a cross section. If you take a cross section here, that is 412 millimeter, overall is 450 millimeter. This is 300 millimeter. Okay. So, if at all you want to cut a bar, you can only cut only one bar. That is the middle one at certain distance from the support. Okay. So, but where exactly we need to cut? It is not going to be at 1/7 of the span. So, if you remember the previous example, we cut 50% of the bars. We had 4 bars in the previous example, out of which we curtailed 2 bars. That means 50%. So, we knew around 1/7 of the span from the support, we will have 50% of the maximum bending moment value. If you remember the bending moment diagram, at about 1/7 of the span, the bending moment at that section will be about 50% of the maximum bending moment. Is it clear? There we can cut 50% of the bars. However, as per the codal recommendation, so that is the theoretical cutoff point. From the theoretical cutoff point, we have to extend the bar for a distance equal to 12 times the diameter of the bar or 1 effective depth, whichever is greater. That's what we did. However, in this case, because we are curtailing only 1 bar, okay, we are curtailing only 1 bar, so the moment of resistance of this section will not be half, instead it will be around 2/3 of the maximum bending moment, that is the design bending moment we take. Then we have to find out where exactly we have to theoretically cut off that 1 bar. Okay, once you find out where you can cut that bar, that 1 bar, from there you extend that for a distance equal to 12 times the diameter of the bar or 1 effective depth. So this requires little bit of calculation, everything. So by keeping that in mind, what I have done is I have ignored it, instead I have continued all the 3 bars into the support. So that way I am using little bit extra material of the steel. Is it clear to you? So that's it for this. Next, so this is done. Check for development length is done. Minimum area of steel, maximum area of steel, and area of the steel is also calculated using the formula. So this step is complete. Okay, what is the next step? To check for shear. To check for shear. So if you remember what I explained before in this module, in the beginning of the module, when it comes to shear, if this is a beam and if this is the support, and of course this beam is subjected to some load. So if you draw the shear force diagram by assuming that this beam is going to be subjected to uniformly distributed load, then this is the way you are going to get this shear force diagram. Okay? So the code says the critical section for shear is going to be at a distance of 1 effective depth from the face of the support. At this section, find out what is the shear force. This shear force is less than this value. Okay? So for this shear force, we have to design and we have to provide shear reinforcement. Okay? However, just to make this one calculation simplified, we can do the clear span, that is from the inside face of the support to the other side. So what is the clear span? 6 meter in this case. So there at that level you can take that shear and you can design for shear at that value. So this value is little bit greater than this. That's okay, because you are designing for shear for a higher value. That way you are going to be little bit safer. Again, to further simplify, what I do is, instead of taking at the face of the support, that is instead of taking the clear span, what I have done is I have taken the effective span, which comes somewhere here. Again, that shear is going to be more than the shear here and here. Again, because I am taking higher value of shear, I am going to be more safe. So that's what I am doing. I am committing an error in calculating the shear, that is the exact shear. Instead, I am taking the shear towards higher value. Okay, that error I am committing is on safer side. Okay, I am doing that just to save time and also to avoid complexity of the problem. So I can go ahead and do everything, but within the given time frame in the examination, if you keep doing all those things, the time will not be enough for you. Just to avoid that, I have taken the effective span and whatever the design load, and I have taken the reaction. Okay, so that reaction is going to be taken as the design shear force. Is it clear to you? Therefore, design shear force VUD equal to WUD LE by 2. Okay, design shear force VUD equal to WUD LE divided by 2. So what is WUD? That is 19.76 multiplied by the effective span 6.412 divided by 2, that is equal to 63.35 kilonewton. Okay, that's what I have written here. So now nominal shear stress tau V equal to VUD divided by BD. So this is as per page number 40.1, page 42. Please open page number 42. Sorry, page number 72. I am sorry, not 42. It is page 72. Okay. So what is VUD? It is 63.35 kilonewton multiplied by 1000. So that is going to be in Newton. So B is the width of the beam, D is the effective depth, which is 412 millimeter. So that is equal to 0.51 Newton per millimeter square. So that is the shear stress developed at the section where we have the maximum shear, okay, due to the design load. So that is 0.51 Newton per millimeter square. So if you go to page number 73 and refer table 20 and compare this value with tau C max for M20 concrete. So for M20 concrete, tau C max is 2.8 Newton per millimeter square. So this is as per table 20, page 73 of the code book. Again, whatever table number I write, whatever page number I write, that is purely for your reference, and you don't have to write these things in the examination. Okay. So because this value 0.51 Newton per millimeter square is less than twice tau C max, then we don't have to go for a redesign of this section. In case this value exceeds 2.8, then the section we have provided is not adequate. So you go back and increase the sectional dimensions and redesign the entire section starting from the bending, shear, etc. Okay. So therefore, no redesign of the section is required. No redesign of the section is required. Okay. So what next? So the next thing is we need to provide stirrups. We need to provide bent up bars. Here we have not provided any bent up bars because we are continuing all the 3 bars of 20 millimeter diameter at the bottom to the support. We are passing it. We are not curtailing and we are not bending any bars. So shear strength contribution from bent up bars is going to be 0 here. So the next thing is, what is the shear strength contribution due to concrete, and also what is the shear strength due to steel. Okay. So here we are not, because we are designing and we know the sectional details and also the percentage of tension reinforcement, we can find out what is the shear, design shear capacity of concrete based on the percentage of tension reinforcement. Okay. And that value is compared with this. If this value is higher than the concrete capacity, then for the remaining load we are going to go ahead and provide stirrups. So let us proceed to calculate tau C value, to calculate tau C. That is the design strength of concrete. So that depends on the percentage of tension steel and the grade of concrete. So go back to page number 72. Okay, look at the top, that is table 9. So just I am going to work on that table. Okay. Percentage of tension reinforcement okay, equal to at the section where we are finding the shear strength of concrete. Okay, not at the midsection. Instead, it is at the support. So, percentage of tension reinforcement at that section is, we have 3 bars of 20 millimeter diameter divided by BD. What is B? 300. D is 412. Okay, multiplied by 100. We are going to get this value equal to 0.75%. From table 19, page 73, table 19, page 73, for M20 concrete, tau C equal to 0.56 Newton per millimeter square. See, for 0.75% steel, we are going to get the value directly from the table. Okay, any value between 0.5 and 0.75 or any value between 0.75 and 1, etc., we have to do linear interpolation. Here fortunately the percentage is 0.75% exact. So, go back to the table. So, there is a value for 0.75 for M20 concrete. The value is 0.56 Newton per millimeter square. That is the design shear strength of concrete. Therefore, shear capacity, that is design shear capacity of concrete. So, if you remember, we have called that as VUC, that is given by tau C multiplied by BD. What is tau C value? That is 0.56 Newton per millimeter square, and B is 300, D is 4112. So, we are going to get this value in terms of Newton. So, I am going to convert that into kilonewton by dividing that value by 1000. So, I am going to get the value of VUC equal to 69.22 kilonewton. That is equal to 69.22 kilonewton. What is the design shear capacity of concrete? 69.22. So, what is the maximum shear force? 63.35. What it means? It means, so concrete itself is good enough to take care of the shear. This is greater than VUD, that is equal to 63.35 kilonewton. Theoretically speaking, we don't need any stirrups. Concrete is strong enough. However, to avoid brittle failure of concrete, so what we do is, we are going to go ahead and we are going to provide some minimum reinforcement as specified in the code. So, here theoretically, we don't need any shear reinforcement. However, we have to provide certain minimum reinforcement as per the codal recommendation. As per the codal recommendation. For that, you open page number 48 of the code book. Please open it. So if you refer 26.5.1.6, we have from 26.5.1.6, page 48. So we have to provide the stirrups in such a way that this condition is satisfied. 0.4 divided by 0.87 Fy, that condition is satisfied. So where ASV is the area of stirrups. Two-legged stirrups means it is 2 multiplied by the diameter of the stirrup bar. B is the width of the beam. SV is the spacing of the stirrups. S suffix V. Of course, Fy equal to 415. So this can be further simplified, and I can write this in the form 0.87 Fy into ASV divided by 0.4 B. I can write that. This is SV less than equal to. That means when we provide the reinforcement, the spacing should be less than or at most equal to this value. So let us use 8 mm dia 2-legged stirrups. 8 mm dia 2-legged stirrups. So by substituting the area of cross section of the stirrups in this section, in this equation, we get SV should be less than equal to 0.87 into 415 into ASV. So we have 2-legged stirrups, that's why I have written 2, and area of cross section of 8 mm diameter stirrup divided by 0.4 multiplied by 300 mm is the width of the beam. So this value I am going to get equal to 302 mm. What it says is we have to provide the reinforcement, shear reinforcement in such a way that the spacing should be less than or at most equal to 302 millimeter. So you can, if you want, you can provide a 300 millimeter center to center or 275 millimeter center to center, 290, anything below this value. Okay, but not beyond 302. But there are 2 more conditions. So again, if you go up on page number 48, so there are 2 lines. Again, go back to the previous page. So 26.5.15, it says maximum spacing of shear reinforcement. So as per 26.5.1.5, page 48, page 47, maximum spacing spacing of stirrups should not exceed it gives two values 0.75 d, that is equal to 0.75 times d is the effective depth, which is 412, that is equal to 309 millimeter center to center, and in no case it should exceed 300 millimeter center to center. So we have three values. The spacing should not exceed 302, which is the spacing should not exceed 309 millimeter center to center, and the spacing should not exceed 300 millimeter center to center. So out of these three values, take the least. What is the least? 300 millimeter center to center. So what is the maximum spacing of the stirrups, two-legged 8 mm dia stirrups? It is 300 millimeter center to center. I am saying maximum spacing. The reason is, if you want to reduce the spacing to say 275, 250 or 225, even 200 millimeter, that's okay. Okay, I am going to repeat, the least of these three values is the maximum spacing of stirrups. So in this case, we are going to provide 8 mm dia two-leg stirrups at 300 millimeter center to center. Therefore, we shall provide 300 millimeter, we shall provide 8 mm dia two-legged stirrups at 300 millimeter center to center. So design of shear reinforcement is over. Next, we'll go with the next step. What is the next one? To check for deflection. Open page number 37 and 38 for that. Please write down. The next one is, I am going to write here. I hope this is complete. To check for deflection. So if you open page number 37 and 38, I am going to refresh your memory. So on page number 37, second column, 23.2.1, it says the vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. So we have the values. For cantilever it is 7, for simply supported it is 20, for continuous it is 26. So ours is a simply supported case. So L by D ratio should not exceed 20. In addition to, for 20 we need to give some correction. So correction due to tension steel, correction due to, or we say modification. So modification due to tension steel, modification due to compression steel, and also modification due to the result of T-section action. Okay, ours is a rectangular section and also ours is a singly reinforced section. So we need to give only the modification factor for tension steel in the tension zone. Okay, so for that What we have to do is, again, if you go to page number 38, if you refer figure 4. So, how to get the modification factor under figure 4? So, first find out what is the percentage of tension steel, that is 0.75%, we already calculated that. Okay. Then find out what is Fs value. If you look at the graph, so just below that graph there is a formula, Fs equal to 0.58 Fy multiplied by area of cross section of steel required divided by area of cross section of steel provided. So from there you can get Fs value. Once you have Fs value on percentage of tension reinforcement, so refer that graph and go horizontally, you get modification factor due to tension steel. So multiply that 20 number, Le by D should not be should not be less than 20. So multiply that 20 by that modification factor, okay, and check whether that condition is satisfied or not. Okay. So as per 23.21.1 page 37, so Le by D should be less than 20 multiplied by modification factor due to tension steel. Okay. So this is 20 multiplied by Ft. Okay, where is 20 for a simply supported beam? Yes, we got this value from there. So what is Le by D? Le by D equal to, so Le is 6.412 is the effective span multiplied by 1000. So it is in millimeter, and 412 is the effective depth provided. So that is equal to 15.56. So I am going to call this as equation 1. So Le by D is calculated. What is the next step? This is Ft, that is the modification factor due to modification factor Ft due to tension steel is what? So we will find out that. So by referring figure 4, page 38, Fs equal to 0.58 Fy, area of cross section of tension steel required, that is area of cross section of steel required divided by area of cross section steel provided, that is the tension steel provided. So that is 0.58 multiplied by 415. Okay. So what is the area of cross section of steel required? If you go back to the area of calculation of steel, AST, what was the value we got? 786.44 millimeter square. That was the value we got. Okay, then we divided that value by the area of cross section of 20 millimeter diameter, that is 786.44 divided by pi by 420 square. We got number of bars equal to 2.5, but we cannot provide 2.5 bars. Instead, we went ahead and increased or provided the bars, provided 3 bars. Okay. So in this case, required as per the calculation was 786.44. Okay. So we provided 3 bars, 3 multiplied by pi by 4, 20 square. Okay. So after calculation, we get the value of Fs equal to 200.8 Newton per millimeter square. That is one thing. That is the Fs value. So what is the next step? What else do we need to get the modification factor? Again, look at figure 4 on page 38. We need percentage of tension reinforcement. Okay, what is the percentage of tension reinforcement? So that was 0.75. Percentage of tension reinforcement equal to 3 bars of 20 mm dia. B is 300 multiplied by D is 412 multiplied by 100, that is equal to 0.75%. Okay. So look here, 0.75 is already calculated. So what you can do is you can directly pick up that 0.75 value from the previous calculation and you can directly write here instead of doing the calculation once again. Okay, for shear, if you remember, we calculated the percentage of tension reinforcement at the support. How many bars we had at this support? We had 3 bars. Even at the midsection, we have 3 bars. So percentage of reinforcement remains the same. Okay. So it is 0.75%. So by referring the graph or figure 4 on page 38, so for 0.75% of tension reinforcement, okay, if you go up for Fs value of 200.8, so I am going to get 0.6, 0.75. I am going to get the value of modification factor equal to 1.25. So some people may get 1.2, some people may get 1.25, 1.26, 1.27. Little bit of variation will always be there when you are reading the graph, but it's okay. Therefore, modification factor, okay, Ft equal to 1.25. Okay, I am going to substitute this value here. So by substituting, the values in equation 1, we get, so what is LE by D? LE by D is 15.56. Okay. So what is 20 multiplied by Ft? Ft is 1.25. That is equal to 25. Okay. This should be less than this. That is 15.56. So 20 multiplied by 1.25 is 25. So 15.56 is less than 25. Therefore, the deflection condition is satisfied. Okay. The deflection check is over. So that is step 6 is over. What is the next step? Reinforcement details. Write down. Next is step 7. reinforcement details. Reinforce. That is 8 mm dia, 2-legged stirrups. Okay, this is 750 millimeter, 750 millimeter. Okay. Clear span equal to 6000 millimeter. Okay. So this is the width, that is equal to 300 millimeter. Overall depth is 450 millimeter. This is 2 of 12 mm dia bars, nominal. So this is 3 of 20 mm diameter. So this is the cross section. Okay. So you take any cross section, AA. It is the same cross section, AA. So this is 8 mm dia, 2-legged stirrups at 300 millimeter center to center. So same thing here, same stirrups. So this is 2 of 12 mm dia bars, nominal. Okay. So this is longitudinal section. Longitudinal section, and this is 3 of 20 mm dia bars. Okay. So this completes the design, and of course this is the effective depth of 412 millimeter, and this is the effective cover of 38 millimeter. Okay. So this completes the problem. So please write down this. This is very important. Any design without a drawing is completely useless. So thank you. We'll take up another example, that is cantilever example, in the next class. Thank you.